So condensation is our next topic for VOC treatment. In condensation, we have conventional systems, refrigeration systems, and cryogenic systems that we will be covering in this video. The types of the condensers, you have direct contact condensers or surface condensers. And what the name suggests, that direct contact, you have two things that are directly together in the same place, or it happens indirectly through the surface. This is an example of a direct contact condenser. In this one, we have the gas is coming down here, and the clean gas is coming out here. So this is contaminated. Contaminated gas is going up here. So what happens inside this condenser? We have spray nozzles that's spraying water. So what happens that this water droplets are going around. What happens when the gas is coming up? It sees this nozzles, it sees this droplets. They are very thin droplets. So the gas is coming up, the droplets are going down. In this interface, so let's say this is your water drop, and now this is the gas coming up, and it has a lot of points, a lot of contaminants that are coming up, right? So these contaminants are moving with the gas. Remember one thing about the VOC, what was it? The VOC partitions between liquid and gas, because that's why it's volatile. So some of this will actually move phase and goes inside the water. What will happen? The water droplets going down, so they will go down. As long as they change phase, they will go down with the water. So now I will collect this water down here. Now I took part of this VOC in the water instead of the gas, and the gas is clean. So this is an example of a direct contact condenser. Any questions? It is actually, okay. Now, if you talk about a thermal oxidizer, you can reach up to 99% removal, or 99.9 even, depending on the design. Direct contact condenser can usually reach 95%, 95%. So, but everyone has advantage or disadvantage. In the other one, you are wasting a lot of fuel. And again, the operation is not easy. You are operating a whole oven. That this one is much easier in operation. And here only the cost of the water. So the water is the cost that you are paying. And if you can recover the VOC from the water, you're actually adding a beneficial cost, because this VOC is money, still it's fuel, or maybe it's a product. So another word for this, by the way, is scrubbers. Scrubbers. You call it wet scrubber. Okay? So some wet scrubbers, for example, that I've worked with in the ethanol industry. In the ethanol industry, it's an industry where they convert corn into ethanol. Ethanol, you know, is the alcohol, and they use it in this as a fuel for cars, additive for gasoline. So now the corn is developed into ethanol, but while we're doing this, you get this gas stream out of the fermentation process where this happens. This gas stream has a lot of pollutants, a lot of VOCs, and they actually treat it with a scrubber. Why do they treat it with a scrubber? Because, again, the gas itself has a lot of ethanol. The main pollutant inside the stream is ethanol, while the ethanol is the product that they're after. So actually, they need the scrubber to recover the ethanol, not for air pollution purposes. Well, it is also for air pollution purposes. They need it, otherwise they don't meet their limits. But they want it more to recover their product. That's an added value for them, rather than to treat the other contaminants. That's a side benefit. So now an air pollution control device becomes part of the process and an air pollution control device at the same time. Does it make sense what I'm? So, okay, now these tanks, they have these tanks, they put corn, okay, and they take it out as ethanol. The gas that comes out of this process has CO2, ethanol, acetaldehyde, formaldehyde, and methanol, and a lot of compounds. So the CO2 is about 98%. Ethanol is about 1.5%, and the rest is 0.5%. Okay, this is an actual case. And really, I have a PhD student, actually, 2 PhD students working on this project in America. So if I burn this stream, if I put it in an oxidizer, I will be burning this ethanol and getting rid of it, converting it into CO2. They don't want that. Why? Because the CO2 is their product. They sell it. It actually has a price. Why would they burn it? So they actually use this one, the wet scrubber. Because by passing the ethanol through this scrubber, the ethanol is recovered back in the water. That's their product. So now they are getting more product. While they are doing this, so that's one benefit, or a very big benefit. While they are doing this, they are also getting rid of other VOCs. That's what I was trying to explain here. We can, but do we want to? We want, because there is always the curve, and that's not for air pollution, that's for life in general. There is the cost of efficiency. Actually, it's costs versus efficiency. In order to reach very low, like if this is 70%, 80%, you will find that the cost that you need is not really too much. But then to reach 90 and 100%, you will find that the cost is much, much higher. So it's always good as an engineer to be in this range where you can get the low-hanging fruit, pay a little money and get really high impact. You don't go there unless you really have to. So if I have to go there, I will not try to improve this and pay so much money to get there. But what I will do, I will use this to get my 80% or 90%, and then take the stream that comes out of it, put it in another process where I can be in this part. So I pay always less money. This is, engineering is always a balance between technicalities and cost. This is what the design is all about. The design is not about finding the best diameter for steel or the best depth for a beam or the best energy for a control device. It's actually balancing the technical. You want to reach your goal, so you reach it while you're doing the best price. Getting the diameter of the steel beam. Why do you want to do that? Because that's the best price. That's the cheapest price. Why do you want to know the depth of the concrete? Because you don't want to use a lot of concrete to reduce the price. Why do you want to make sure that the energy also to reduce the price? So it's always a mix between reaching your goals technically while maintaining the best price. Any questions? So another design will be the ejector condenser. Here you have your inlet stream coming from one side, and then you have high pressure nozzle, and then the discharge of the liquid comes this way together with the air. So now they are going co-current versus counter-current. Just another design. Shell and tube condenser. Now the shell and tube condenser has a different idea. Here we are cooling, okay, we are cooling some pipes. So we are reducing the temperature of some pipes. And then we let the contaminated gas go around these pipes. Very similar to the idea of, do you remember in the previous video? Recuperative thermal oxidizer, where we were heating up the gas by passing it through hot tubes. Now we are cooling down the gas by passing it through cool tubes. Okay, and it keeps you put baffles. These are called baffles, and the idea of the baffles is to make sure that the flow has to go through one pass. So it will go through a long pass, not just go in, go out. By the time it comes here, most of the VOCs will be out of the stream. Why? Because they condense. When we decrease the temperature, a lot of the VOC will turn into liquid and fall down, leaving the air to go with much lower VOC content. So this is another way of controlling your VOC with the shell and tube condenser. Now this is a direct contact. That's the other one, right? Surface condensers. Another design, there is the tube and fin condenser. We don't really have to go there, but it's all about the surface area now. Because again, similar to what we talked about earlier, the higher the surface area available for the contact, the more efficiency you can get. Will not go really through the refrigeration cycles. You can, if you're really more interested in this, you can look at them, but we as civil engineers, we don't really go too much into that. Now, cryogenic systems, they basically depend on something like liquid nitrogen. What is liquid nitrogen? Very cold water. Nitrogen, I'm saying. Liquid nitrogen. So you've seen it, the liquid nitrogen. So it is basically nitrogen, that like how we have in the air, but it's cooled so much that it turns into liquid, similar to the water, right? When you heat it to the boiling point, it becomes into gas, right? So the nitrogen in our room temperature is gas, but if you cool it below its boiling point, which is really, really low, it turns into liquid. So liquid nitrogen, why do we need it for? Liquid nitrogen, we use it when we want to have instantaneous cooling. For example, I have this very hot tea and I want to cool it in a second. I throw it inside liquid nitrogen. Suddenly, it is at negative 200. So that's the idea. Or if you, for example, they use it also to store samples for a long, long time. because you cannot just keep, for example, biological samples if you want to or DNA samples for quartz and so on. You don't want to keep it for in a freezer -80 and keep paying electricity for the -80 because that's a very powerful fridge. So basically what they do, they put containers that can keep the cold as much as possible without very minor losses, and then they put the samples inside with liquid nitrogen inside, and they close it. So these are all uses of cryogenic systems. So not only nitrogen, by the way, that can be used. You can also get liquid helium. You can get liquid hydrogen. You can get liquid a lot of things. So depending on the use, but liquid nitrogen, again, it's one of the most used because of the property of nitrogen that it's a noble gas. It doesn't react. And that's what you want, right? You want to decrease the temperature without any reactions. I'll not go into this, but I'll just want you to understand that while we are pumping gasoline into the station, not when you are pumping your car, but when they are actually filling the station itself with gasoline for you to use later, there is a lot of losses of VOCs that happen because you are putting now a VOC or gasoline that's liquid into a tank that's mainly gas. It's empty, right? While you are doing this, the pressure, right, it's increasing, and a lot of gases are evaporating, so you get a lot of losses while doing that. So the EPA actually has a whole rules for filling and emptying of gasoline tanks. And this is a whole, like people do it only in their career. Not only for gas stations, but you can think about it when you are doing oil and gas extraction, when you are extracting it from the field, and then you are filling all these very large tanks. Same thing happens. Also when you are emptying the tanks, because you are creating negative pressure. A negative pressure means that a lot of evaporation will happen. So VOCs really play a very important role in our life. We just don't really realize how much. I will not go there as well. I don't really, it's the mathematics design of VOC equipment, including absorption, is really sophisticated. So if I will ask you problems, I will really be very like problems about basics rather than about this. If you're interested, you can look at the slides, you can discuss them together, but I think they are beyond the levels of the class. I will stop here for this video, and next video we'll be talking about the biological bioreaction, and that includes biofilters, biotrickling filters, and bioscrubbers.